Alright class, so going to talk about vascular resistance to blood flow. The basic concept that I want my students to understand here is that if there is more resistance, you will have less blood flow, less flow. So more resistance, less flow. That's the concept. Okay. Now, as the ventricle pumps blood, the blood goes into the aorta, right? Remember that the aorta is a very, very elastic artery which can stretch in order to withstand the high blood pressure coming out of the ventricle. And the aorta will then branch and then carry that blood to different organs of the body. Do you agree? Now, as blood flows through different organs, the blood experiences different amounts of resistance from different organs. Meaning, let's say blood goes to one organ and that organ lets a lot of blood to flow through. So that organ provides very little resistance to blood flow, right? As opposed to that, let's say blood goes to another different organ and that organ does not let a lot of blood to flow through. So that organ is providing, or that organ is imposing a lot of resistance to blood flow. So you have to understand that the cardiac output is distributed unequally to different organs, and different organs provide unequal resistance to blood flow. Okay, so different organs provide different amounts of resistance to blood flow. All right. Also, let's say we have a blood vessel here. This is a blood vessel, and at this end the pressure is, let's say, 150 millimeter of mercury, and this end the pressure is 20 millimeter of mercury. Do you see a difference in pressure? Yes, you do. So the difference in pressure is denoted as delta P. That's the difference in pressure. So when you have a difference in pressure, you will have blood flow from high to low. So blood will flow this way from high pressure to low pressure. If there is no difference, let's say you have a blood vessel and you have 100 millimeter of mercury pressure here, and you also have 100 millimeter of mercury here. So pressure at both ends of the vessel is same in this case. Do you think there will be blood flow? No. So you will have no flow in this case. So obviously you need a pressure difference for blood to flow. Know that. Also, the rate of flow is directly proportional to the difference in pressure. Meaning, if the pressure difference is too high, let's say 150 versus 20, right here, as you see in this example, you will have a faster flow. Now let's take another example. Let's say this is another vessel. This is another vessel. The pressure difference, let's say this is 150 and this is 100. So this will have a slower flow of blood because the pressure difference is not that steep. Got it? Okay. Now let's look into the diagram on the right hand side. This diagram, you see a box, right, with 4 chambers. So obviously this is your heart. And also you see a tube. So that tube is actually representing your aorta leading to the systemic blood vessels, and then the blue end is representing the superior vena cava. So this is the aorta that carries a lot of blood from the left ventricle, distributes it throughout the body and gets deoxygenated, and then the blood returns to the right atrium via the superior vena cava. Okay, so listen carefully, as the left ventricle pumps out blood, the aorta, so all that blood from the left ventricle gushes out into the aorta, right? Remember, aorta is super stretchy. So the aorta stretches out to withstand the high blood pressure. And when blood gushes into the aorta and stretches the aorta, we call that our systolic blood pressure, which is about 120 millimeters of mercury, right? Then eventually that blood will flow from this high pressure area to these areas which are low pressure. So blood will flow as shown by the black arrow here. And as the blood flows out, we will have relaxation of the aorta, and that pressure is the diastolic blood pressure. Do you agree? And the diastolic blood pressure is 80 millimeter of mercury. If you add those two and divide by 2, so 120 plus 80 by 2, you get the mean pressure. So the average is 100 millimeter of mercury, right? That's the average number we get, which is shown. Let me see if I can change color. Yay, I can. Awesome. So this is the mean pressure on the aorta. It's 100 millimeter of mercury. So we can say that at this point, the pressure is actually 100 millimeter of mercury. All right, now what is the pressure at the superior vena cava here? Very, very low. It's about 0, no pressure, 0 millimeter of mercury. Therefore, what do we see here? What's the point, Rupa? The point is we do see a huge pressure difference. We see 100 millimeter of mercury pressure at this end, 100, and at this end we have 0, right? So there is this huge pressure difference between the two ends of the vessel. And if you calculate the delta P, which is the mean arterial pressure, delta P is also MAP, or the mean arterial pressure. That comes out to be 100 millimeter of mercury. 100 minus 0, that's 100. So there is a lot of pressure difference, right? So this pressure difference will allow the blood to flow, get distributed throughout the body, throughout all the vessels, and then the blood will ultimately return to the right atrium. Okay? All right. Vascular resistance. So this is another way of talking about the basic concepts here. And we already know that if we have, we already know that flow depends on resistance. More resistance, less flow. Less resistance, more flow. We know this. And now you do see some formulas here. Don't get intimidated. I just want you to understand the concepts, and you will be tested on understanding concepts, not on formulas. I want you to look at this formula right here. What do we see here? We see that resistance and blood flow, let me see if I can change color. Yay. Resistance and flow are inversely related, right? That's exactly what we talked about. More flow means we have less resistance. Less flow means we have more resistance. Okay. And delta P, as I said, is the mean arterial pressure, which is the pressure difference between the two ends of the tube. Hope you understand that. Now there is some, now you will ask me, Rupa, what determines the resistance? What is this resistance and what does it depend on? Where is it coming from, right? We want to know those things. I do not want you to memorize this. Please do not memorize. Do not memorize this. Please don't. Okay. But I want you to understand that resistance depends on few things. Resistance depends on the length of the vessel. The longer the vessel, the more the resistance. So, more increase in length means that equals to increase in resistance. Resistance also depends on the viscosity of the blood. Now, let's say you are very, very dehydrated. Will your blood get more viscous? Yes, it will. So, as the viscosity increase, that increases resistance. Obviously, the blood is thick now. Obviously, it cannot flow super fast. Does that make sense? Blood is sticky. It cannot flow fast. So if you have if you have increase in viscosity, which is denoted by this, then you will have increased resistance. Makes sense. And if you have increased radius, so if the radius increases, meaning let's say you are looking at a thicker blood vessel. So if you have increased radius, that decreases the resistance. So resistance and radius are inversely related. And length and viscosity are directly related to resistance. Okay, I want you to remember these. All right, so this is another graph showing pressure on the y-axis and resistance on the, what is this, x-axis. Okay. So what do we see? Essentially, what we are trying to see is that blood is being pumped out of the left ventricle, right? So this is the left ventricle that is pumping out the blood. So a lot of pressure there. Pressure reaches about 120 millimeters of mercury. Larger arteries like the aorta, brachiocephalic trunk, the right common carotid, those arteries withstand a lot of pressure. Remember, those are elastic arteries. They're very, very elastic. So they can withstand a lot of pressure, and the pressure in these arteries are about the same, 120 millimeters of mercury. As these arteries branch into muscular arteries and other arterioles, you see that the pressure drops. Do you see a drop in pressure? And then at the capillary, the pressure is too low. And remember, that is important because of good exchange. You want there to be good exchange of material. So low capillary pressure is what you want. That is good. And when you reach the veins and the venules, the pressure is too low. And we talked about this before. This is just another representation. All right. So pressure generated by the beating ventricles is largely dissipated. I want you to understand that. So the pressure kind of dissipates away by the time the blood flows further away from the heart. So the more you travel, or the more further away from the heart, the lesser the blood pressure. And we have seen this in lab. Remember, we did talk about that if you take blood pressure at the femoral artery, the pressure will be significantly low. The number of beats and the heart rate will remain the same. The heart rate will remain the same, but the pressure will be low because femoral artery is further away from the heart. And by the time blood reaches the femoral artery, the pressure is too low. And that's why we always take blood pressure on the brachial artery, which is in the upper arm and which is close to the heart, right? Because we can get a good blood pressure in the brachial artery. It's the same concept. I'm just showing you in a graphical form. That's it. I'll stop here. Oh no, actually I can do this one too. So let's talk about total peripheral resistance. So total peripheral resistance is the sum of all vascular resistance in systemic circulation. So let's talk about this real quick. So this vessel, do you see this vessel? That represents the aorta. And we do see these branches coming out, right, in red. So know that, and these branches carry oxygenated blood to different organs. I'll stop here and then start with a new video because it's almost 15 minutes.